Have you ever wondered if there's one single rule that governs, well, everything? From a star exploding, to you kicking a soccer ball, to your phone charging? It turns out there is. It's the law of conservation of energy, and it's the most fundamental rule in the universe. Think of it this way. All the energy in the universe is like a giant fixed set of Lego bricks. You can't make new bricks, and you can't destroy any bricks. All you can do is take them apart and build them into something new. You can change a Lego castle into a Lego spaceship, but the number of bricks stays exactly the same. Energy works the same way. The official, sciencey way to say this is, energy cannot be created or destroyed. It can only be transformed from one form to another. This means the total amount of energy that exists right now is the same amount that existed at the Big Bang, and it will be the same amount forever. When we use energy, we're not using it up or destroying it. We're just changing its costume. So what are these costumes that energy wears? The main two you'll hear about in physics class are potential energy, which is stored energy, and kinetic energy, which is the energy of motion. But there are many others. Chemical energy is stored in the bonds of your food or a battery. Thermal energy is heat. Electrical energy is what's in the wires of your house. Light, sound, all of these are just different forms of the same one thing, energy. A roller coaster is the most classic example, and for good reason. Imagine you're at the very top of the highest hill, just before the drop. You're high up, but you're barely moving. You have maximum potential energy. Then you drop. As you fall, your height and potential energy decreases, but your speed and kinetic energy increases. At the very bottom, you have zero potential energy, but maximum kinetic energy and maximum speed. The energy just changed from stored to motion. A pendulum is just a roller coaster on a string. When you pull the pendulum bob all the way up, it stops for a split second. At that high point, it has maximum potential energy and zero kinetic energy. When you let it go, it swings down faster and faster, and at the very bottom of its swing, it's moving its fastest. That's maximum kinetic energy and minimum potential energy. The energy just keeps transforming back and forth, from potential to kinetic and back again. This is the big question every 8th grader asks. If energy is conserved, why does the pendulum eventually stop? Why does the roller coaster need a motor to get back up the hill? Did you just destroy the energy? No, the energy just transformed into costumes that weren't useful. Friction in the pendulum's hinge and air resistance robbed the motion, converting that kinetic energy into tiny, tiny amounts of thermal energy, heat, and sound energy, the swoosh of the air. If you could measure it, you'd find 100% of the energy is still there. It's just not motion anymore. Let's drop a basketball. When you hold it at shoulder height, it's loaded with potential energy. When you let go, gravity converts that potential energy into kinetic energy as it speeds up. Then, thud, it hits the floor. What happened to all that kinetic energy? It was instantly transformed. You heard the sound energy. The floor and the ball vibrated and got ever so slightly warmer, creating thermal energy. And the ball squashed and sprang back, which is elastic potential energy. No energy was lost, it just scattered. You are a walking, talking example of energy conservation. You eat a sandwich for lunch. That sandwich contains chemical energy stored in the bonds of its atoms. Your body's metabolism is like a tiny power plant. It burns that fuel, breaking the chemical bonds and releasing the energy. It transforms it into kinetic energy so you can run, walk, and live. And it also releases a ton of thermal energy, which is why your body is a cozy 98.6 degrees. A bonfire is a much faster, more chaotic version of your metabolism. A log of wood is just stored energy. It's packed with chemical energy that trees stored from the sun years ago. When you add a little heat, activation energy, you start a chain reaction. The wood burns, and that stored chemical energy is rapidly released as thermal energy, the intense heat, and light energy, the bright flames. The energy isn't made by the fire. It was unlocked from the wood. Those little disposable hand warmers are a perfect, self-contained chemistry lab. Inside, there's a pouch of iron powder and other chemicals. They are full of chemical energy. As long as they're separate, nothing happens. But when you crack it, you mix the chemicals and let oxygen in. A chemical reaction called oxidation, rusting really, starts, and it's exothermic. That means it releases its stored chemical energy as thermal energy, heat, right into your cold hands. Let's follow the energy to your phone. Far away, a power plant burns coal, releasing chemical energy as thermal energy. That heat boils water, creating steam. The steam's kinetic energy spins a giant turbine. The turbine, more kinetic energy, spins a generator, which converts the motion into electrical energy. That electrical energy flows through hundreds of miles of wires, into your house, into your charger, and is finally stored as chemical energy again. Inside your phone's lithium-ion battery. What a journey. Now let's use the phone. You unplug it. The battery starts to discharge, converting its stored chemical energy back into electrical energy. That electricity runs the phone's processor, which does two main things. It sends energy to the screen, which transforms it into light energy so you can see your texts. And it sends energy to the speaker, which transforms it into sound energy so you can hear your music. And as you know, all the parts working together transform some of it into thermal energy, which is why your phone gets warm in your pocket. An electric fan is one of the simplest examples you can see. You plug it in. Electrical energy flows from the wall. The motor is a device designed to do one job: transform that electricity into motion. It converts the electrical energy into kinetic energy as the blades spin. Of course, the conversion isn't perfect. You can also hear the sound energy of the whirring, and if you touch the motor, you'll feel the thermal energy, waste heat, it generates. A car's internal combustion engine is a powerful but very inefficient example. Gasoline is full of chemical energy. An explosion in the cylinder converts it into kinetic energy to push a piston. This eventually turns the wheels. But where does the rest of the energy go? Most of it, about 75%, is transformed into thermal energy, waste heat, that has to be cooled by the radiator and pumped out the exhaust. And you also get a lot of sound energy, the engine's roar. All the energy is conserved, but most of it doesn't even help the car move. A solar panel does something truly amazing. It captures light energy, also called radiant energy, that has traveled 93 million miles from the sun. The photovoltaic cells inside the panel are made of special materials. When sunlight hits them, it knocks electrons loose. This flow of electrons is electricity. So, the panel's only job is to transform light energy directly into electrical energy, with no moving parts. This is the most important energy transformation on Earth. It's how energy enters our living system. A plant uses photosynthesis. It takes light energy from the sun and in a complex chemical reaction, transforms it into chemical energy, storing it in the bonds of a sugar molecule. The plant then is that stored energy. When a rabbit eats the plant, and a fox eats the rabbit, and you eat a carrot, you are all just transferring that original solar energy, which was conserved in chemical form, up the food chain. A hydroelectric dam is just a giant man-made roller coaster that uses water. The water held back in the reservoir, high up behind the dam, is like the coaster car at the top of the hill. It's full of potential energy. When the operators open the gates, the water falls. That potential energy transforms into kinetic energy as it rushes down the pipes. At the bottom, it slams into a giant wheel, a turbine, and its kinetic energy forces the turbine to spin, which generates electrical energy. A simple light bulb is a great way to understand energy waste. You feed electrical energy into it. You want light energy. But the bulb also produces a lot of thermal energy, heat. An old incandescent bulb was basically a heater that accidentally made some light, transforming 90% of its energy into heat. An LED bulb is much more efficient. It transforms 90% of the electrical energy into light and only wastes 10% as heat. But in both cases, 100% of the energy is conserved. So the big takeaway is this. The law of conservation of energy isn't just a random fact for a test. It's the bookkeeping system for the entire universe. Energy is the currency, and this law says no money is ever added or taken away. It just changes hands and changes forms. It explains why the world works. You have to eat to move, a car needs gas to run, and a ball eventually stops bouncing. Nothing is magic. Every bit of energy is, and always will be, accounted for.